So, I am Valentin. Hi. Thank you so much, Jimmy, for your patience and for hosting me in the first place. I am very excited to speak here. Thanks for having me. I will present our paper, HouseLayout3D, a benchmark and training-free baseline for 3D layout estimation in the wild. This was the result of my master thesis, supervised by Francis, formerly at Stanford, and Marie-Julie at Google. Myself, I'm based in Zurich and I studied at ETH. So we are looking at the task of 3D layout estimation. Here, the goal is to abstract a scene into a compact vectorized 3D representation. Concretely, we start from a set of RGB images and recover the key structural elements of the space. That is, walls, floors, and ceilings, along with doors, windows, and stairs. Importantly, we care about recognizing entities. So a wall should not just be a random triangle mesh, it should rather be a planar rectangle or a simple polygon, so you can actually edit it and then later reason about it. Despite its wide range of applications, we find that 3D layout estimation for complex multi-floor buildings remains largely underexplored in academia. We therefore introduced the HouseLayout3D dataset, a benchmark of large, architecturally complex, real-world layouts. We also introduce a baseline method that outperforms state-of-the-art methods by leveraging recent progress in 2D segmentation and 3D reconstruction. Our method is at the heart very simple. You first reconstruct the scene, then you use 2D pre-trained segmentation models to get a semantic segmentation of the reconstruction. Then you remove everything that you believe should not be part of the actual layout, and you fit the layout to the walls, floors, and ceilings that remain. Traditionally, people will tackle layout estimation by first making some very strong assumptions about the scene that you are reconstructing. Typically, you would make a Manhattan world assumption or something similar. Then you take an individual image or panoramic image and you predict something in 2D. There would be key points, or maybe you do a segmentation. And then you can use your strong assumption to assemble these 2D predictions to a 3D layout. More recently, there has been an emerging field of end-to-end trained layout detection models. So this means end-to-end train means that you start with the point cloud, maybe you extract some features, maybe not, and then you train a transformer or different deep learning method to directly output a floor plan, a 2D floor plan in this case. An example of this would be RoomFormer. Taking this even further, there's been a very exciting paper that maybe some of you even know, that is SceneScript. They have a similar end-to-end approach as RoomFormer, but they are directly predicting 3D entities from point clouds. So for the layout part, what they're doing is they're predicting 3D rectangles with semantic labels, being walls, windows, or doors, that then represent to some extent a layout. However, those end-to-end trained methods are limited by the data they are trained on. If we look at existing layout estimation datasets, they typically suffer from one of three fundamental limitations. Firstly, many only provide a 2D floor plan annotation of the scenes. Secondly, when they do provide 3D layouts, they often predominantly consist of small single-room scenes, like SceneCat here in the middle, for instance. And thirdly, when scenes do get bigger, data is typically synthetic. And synthetic datasets, as you probably know, they do scale well in quantity, but they struggle to scale in diversity. So they tend to be structurally simple because modeling diverse, large, multi-floor buildings, it's very expensive and time-consuming. Also, those synthetic datasets typically don't contain those random little sensor artifacts that we usually struggle with in computer vision, such as, for instance, artifacts around windows. Now, the absence of suitable datasets for training has led to existing methods often failing when being applied to large real-world buildings, even when we apply them on a per floor or per room basis. Here on the right side of the slide, what you see is the method RoomFormer being applied to a Matterport scene where we applied to each floor separately, and still it fails. So summing this up, they typically fail because either the assumptions they were built on, such as the Manhattan world assumption, does not apply to the real world scene in question, or because the synthetic data that they were trained on just looked fundamentally different than the real world example they are struggling with now. This can be because the room size doesn't match, because the model has never seen a skewed ceiling, or has never seen a gallery either, as you can see here an example of, for instance. All right, so therefore we introduced this new HouseLayout3D benchmark dataset of architecturally challenging buildings that highlights this shortcoming of existing methods and datasets. Our dataset is built on Matterport 3D scenes. Matterport 3D, maybe you know it, is a collection of building scans. The building they scan is, well, how should I call it? Sometimes a bit eccentric. They have a lot of large and complex buildings. And this collection of scenes, it already comes with a lot of features. It comes with 3D reconstructions. It comes with 2D images, RGB and depth. And it already has some semantic layers. So you already have a 3D instance segmentation of objects. Now, what we do in our work is we add a layer of semantics on top of those existing scenes, meaning that we annotate scenes with layout annotations. We annotate the structures, the walls, floors, and ceilings, as well as the important layout semantics such as doors, windows, and stairs. Altogether, we annotate 16 scenes with 300 plus rooms featured in 26,000 RGBD images. Very importantly, in our annotations, the entities, meaning for instance, the doors and the windows and the walls, they are simple polygons and they're all hand annotated. Of course, the dataset may not seem super large at first, but it is actually comparable in terms of rooms, at least, to the validation sets of ScanNet or ScanNet++. In addition to the dataset, we also introduce a baseline method, multifloor 3D, which generalizes to those large scenes by leveraging pre-trained 2D segmentation models and a novel 3D layout fitting technique. Remarkably, we do not require any layout-specific training, and we outperform state-of-the-art methods on our dataset still. All right, so let's go and get a bit more technical. I'll explain the multifloor 3D pipeline to you. Just as a reminder, we start from 2D images, from RGB images, and we want to get a layout that essentially consists of simple polygons and some semantic information such as doors, stairs, and windows. The pipeline consists of 4 main steps. We start very simply by reconstructing the scene and extracting a mesh. In doing so, we follow exactly the procedure of D-end splatter, depth and normal splatter. This is a variation of Gaussian splatting that adds depth and normal priors. From the reconstruction, we extract the mesh. There we also follow D-end splatter. They essentially back project, diffuse depth, obtain a point cloud, and apply a Poisson measure to the point cloud to obtain a mesh. Once we have the reconstruction, we run a 2D segmentation model on all of the 2D frames that we used for the reconstruction in the first place. We do this to remove objects and furniture. Concretely, we run the one-former model. It predicts COCO classes. We subdivide those classes into keep classes, so to say, and throwaway classes. And once we have this segmentation in the images, we project it to the mesh. We fuse it in 3D, and then by majority vote on the visible perspective, essentially, we segment the mesh. And the output of this is what we call a layout skeleton. And this is a mesh with holes, if you want. It is the backbone of the mesh, the part that we really want to have in the layout that we do not remove. All right, now the juicy part comes. From this layout skeleton, we want to obtain a more complete layout, a layout prototype, as we call it, something that does maybe not yet have the stair, window, and door annotations, but we definitely want to close those holes and connect the walls to the ceilings and the floors and simplify this into a layout, hopefully obtaining a cleaner, compact representation of those structural elements. Now, how did we do that? Well, we cast this as an optimization problem. What we are optimizing is a set of planar polygons. So we optimize the vertex positions and plane equations of a set of polygons, where for each polygon we constrain the vertices to adhere to the polygon plane equation. So we start by initializing a initial set of polygons. On the left, you see the initial mesh. Then we remove the bed and stuff, and then we run a very simple sequential ransack algorithm to obtain a set of polygons that is good for starters, and that we now want to simplify using a optimization objective. Now, this optimization objective has three parts, and they are meant to mathematically express how I was describing the layout to you previously. Essentially, we want it to be connected, we want it to be simple, and we want it to be geometrically consistent with the layout skeleton. So how did we formulate this? Let's go through step by step. First of all, the connectivity loss. So what it states is that polygons attract vertices. It essentially penalizes the distance between a vertex and the surfaces of nearby other polygons. That is, we implement a vertex polygon distance, that is the distance of a vertex to the closest point that lies on the surface of another polygon. So with that, we create like a magnetism mechanism, hoping that if you have a wall that almost goes down to the floor and a floor that almost reaches the wall, that they will grow into each other by attracting each other. To make this a bit more stable, we also add a cutoff for very large distances that we don't have global attraction in large buildings. Secondly, we have the simplicity loss. And what it says is that edges that are not shared between multiple polygons should be as short as possible. So essentially, the thought behind this is that we distinguish between edges that are, in our mind, clean because they are shared between multiple polygons. For instance, an edge that is between a floor and a wall is essentially the intersection of two planes, and it's very likely to be one that we want to keep in the model. Whereas an edge that is just loose somewhere in a random place, we are inclined to try to eliminate it, to shrink it, and to actually force the other edges, the shared edges, to express the entire scene. So essentially, the loss term here is just the length of the non-shared edges. All right, then lastly, we have a geometric consistency loss, which ensures that the estimated layout remains consistent with the layout skeleton that we started with. It comes in two terms. It has a proximity term, which essentially says that every vertex of the layout skeleton should be close to the layout, to the estimated layout. So essentially, in this layout skeleton, there should not be any vertex that is kind of forgotten, that is not covered by the estimated layout. And we implement this again using the same point to polygon distance as with the magnetism mechanism before. And the second one is that the layout must not intersect with the observed empty space. Now, what does that mean? It's a bit abstract to formulate. I called it also the ray tracing distance. And essentially what it does is that we have this mesh, we have a lot of camera positions, and for every camera position, for every view, we have a depth image, a fused depth image. Now, from this, we can sample a bunch of rays. So essentially from the camera to the point in space where the depth points us, we can mark the observed empty space, meaning that this is something that we have seen through, space that we've seen through from our cameras, and therefore also space that we believe should not be occupied by the layout. Now, why is this necessary? If you take a door, for instance, a door is a concave space, and if you just try to shorten all the edges and simplify everything, the door will be forgotten unless there is something that is actually blocking this door. As you can see here, there are a lot of rays going through the door, and those rays will tell the model that here you cannot have polygons, you should keep this door open. So what we concretely mathematically penalize is the intersection between the layout, polygons of the layout, with such rays. All right. And those are the two subterms that make up the geometric consistency loss, and that already completes our optimization scheme. Time to look at some images. As you can see, maybe you didn't see it, I will play it again. As you can see, you see how slowly the in the beginning quite fractioned and complex polygons gradually merge into something simpler until in the end there are very few very clean polygons left. Now, two things that you might have observed here already during the explanation. Actually, the simplification, the optimization doesn't really reduce our vertex count. To really reduce the vertex or polygon count, what we do is that we merge very close vertices. Essentially, when vertices collide, then we remove the duplicates and we merge very, very similar coplanar polygons. Also, you might have noticed, or you might notice now, a jump in the convergence of this model. And this is because we use a little trick to accelerate the convergence. And the trick is that we removed the objects before, right? So now we just simply project those objects to the nearest floor if it doesn't increase the loss. And also we extend the walls to the floors and the ceilings if it doesn't increase the loss. This is possible because we do have those semantic labels from the 2D segmentation, so we can simply use them to add a bit more engineering if you want. All right, this gives us the layout prototype. This is a barebone layout. It's still missing doors and windows, but we're almost there. Now, in the next last step, what we're going to add are those missing components, as I said, but also a concept of interior and exterior space. So far, we don't have any guarantees that we have produced a waterproof mesh. We don't have any guarantees that a room is actually a closed concept. All we have is a hopefully connected point set of polygons. So what we do is we apply an existing methods for scene graph parsing. It's called HouseLayout3D. It uses vision language models in combination with morphology, and it gives us a segmentation of our layout into rooms connected by edges being doors or stairs. Those are also the final labels of our layout directly produced by this method for doors and stairs. This step also helps removing artifacts. Sometimes you have outdoor areas that are also reconstructed. So if we get a room that is called garden, we just delete it. All right. Now to get this interior versus exterior space, to get this closed shell, we do a final somewhat optional processing step. We look at each room individually and we extrude the floor to the ceiling. Meaning for the room, we identify the floor polygon and the potentially many ceiling polygons, and then we subdivide the floor into a triangulation. And for each triangle, we simply cast a ray upwards to identify the ceiling polygon. And then we simply grow this triangle upwards, meaning that we connect it with walls to the ceiling. With that, we ensure that every room is by itself a closed space, and we do not have any holes anywhere. And we actually create the notion of space, not just of random polygons floating in thin air. All right, and lastly, very simple, we need to add the windows too, and we simply back projected the 2D predictions onto the walls and then created the windows from that. The output is a set of floors, walls, ceilings, stairs, windows, and doors. All right, so let's go to the results. We evaluate our method, of course, on the presented dataset of large complex scenes, and we compare it to the recent methods we talked about, to RoomFormer and SceneScript, both of them being end-to-end trained. However, those methods do not work at all out of the box for such large scenes, such as in HouseLayout3D. So we apply them per room instead of per building, meaning that we use prior information for the other compared methods that we do not use for our model. For RoomFormer, which is a 2D methods, we additionally need to estimate the height of the room to be able to extrude it to 3D. All right, as you can see, the baseline methods often struggle despite the additional prior information. In particular, they struggle with the sizes of the rooms and some artifacts that are from outdoor spaces, as mentioned previously. What this ends up with is essentially a little room floating there out somewhere because there was some lost point that was out there in the reconstruction. You might also notice that SceneScript, top right, is looking a bit different than the others. And that is because what it predicts is essentially a set of 3D rectangles. And to the best of my knowledge, there is no way to get any notion of indoor or outdoor space. And by extension, also no concept to get the orientation of the walls. So we cannot enable this backface culling, which we have in the other visualizations here. All right, so how do we evaluate this? We use the established, proposed by SceneScript, entity alignment score. This is essentially a F1 score on a matching between ground truth and predicted entities. That means that we say that two entities from prediction and ground truth are matchable if they fall within threshold distance of each other, meaning that all of the vertices are within threshold distance to the surfaces of the other polygon. And then on this matching, we can compute the F1 score and measure this for different thresholds. As an other somewhat alternative metric, we also measure the layout depth error, which essentially says that you have your perspectives and you can back project the depth of both the ground truth layout and the predicted layout. And then you can measure the difference between those two estimated depths. And if the error is smaller than a given threshold, you give it a point, and if you don't, you give it no point. All right, so what we find in our evaluation is that with respect to this entity alignment score, we significantly outperform both RoomFormer and SceneScript. Also, we are the only method that also predicts stairs. They are left out on this graph, but yeah. And structures, those are the walls, ceilings, and floors. However, this graph looks very good for us, I think, for a start, but it is really not something to brag about because the scores here overall are really low. So even if our method is a lot better than the others, we only actually manage to align those entities in about 35% of the cases, which is still very low. There's a lot of potential here, a lot of work to be done to get better at those scenes. We also evaluate our method and the other methods on Scannet++. Those are very small scenes, but they're very interesting, we think, because they are captured with an iPhone. And we believe that this is a very cool and common use case for layout estimation to do it based on a phone. So here our method also demonstrates quite robust performance. It outperforms both SceneScript and RoomFormer in terms of this projected layout depth that I explained previously. We can only evaluate this layout depth here, or approximate it even, because those scenes don't actually have ground truth annotations. But what we can say or claim is that we can measure the back projection error on the walls and the floors and the ceilings because they do have semantic annotations on those. And when you see a floor or when you see a wall, then your layout should definitely be close to that wall. It should just be simpler, of course. All right, and then as a little toy application, we also showcase that you can use this scene graph for navigation, for instance. So you essentially translate this into a JSON format and you ask ChatGPT, how do I get from A to B? And it will be able, because it is a connected scene graph, because it has those notions of indoor and outer space, you will be able to get like a navigation plan, how to get somewhere. Okay, and that is more or less it from my side. I have a bit of a private opinion that I can also, or a note of reflection on this that I want to share. And that, as you have probably noticed, this is a very engineering heavy method. There are a lot of components, there's a lot of modularity, which has some advantages. You can exchange components if you want, but it's also a trade-off, right? If you make an error in the first step, you will propagate this error until the end. So what I'm really trying to say here is that I believe there is a very important contribution that we made with the dataset, with pointing out that we should really take this problem to the real world. We should stop playing with those small datasets and we should actually try to make this actually useful, because I think we are, that reconstruction is there, and I think layout estimation should be soon there too. So I really hope that our dataset encourages other researchers to tackle this problem, and I don't think the bar is astronomically high. Yeah, and that's it. You can find the dataset on our webpage.